Hey everyone, welcome back. Today we're going to look at concentration, this time for percent by volume and then the mole fraction. So percent by volume, similar to what the name would suggest, is just a percentage in the context of volume. So the percent by volume, which will give us an indicator for how much solute is present in the entire solution, but this time with respect to the volume, is just the volume of the solute divided by the total volume of the solution times 100. This is very similar to percent by mass, with the only exception being that it's just a different context of the measurement, mass, except for volume. But the approach doesn't change, it's still a percentage, still one part out of a whole. So let's see an example of how percent by volume can be used. What volume of water should be added to 12.5 milliliters of isopropanol to obtain a solution that is 15% isopropanol? So in this case, we're looking to find the amount of water that we're trying to add to get this certain percent by volume of our solution. So our percent by volume, which in this case we're targeting a 15% isopropanol solution, is going to be the volume of the isopropanol, which we know that we're aiming for 12.5 milliliters of it, and its total volume of the solution. So if we rearrange this, we see that the volume of the solution is just 12.5 milliliters divided by our 15%. So our solution would be 83.3 milliliters. Now this is where we want to be careful, because this is the volume of the solution, but we're asked specifically how much water is there. So the solution's got two parts. It has the solute and the solvent. The solute, in this case isopropanol, and the solvent of water. This 83.3 is of both isopropanol and water. This question is specifically asking us to find just the volume of the water. So we already know that our entire solution is 83.3 milliliters. And since we know that we are going to have 12.5 milliliters of the isopropanol, well, that must mean there are going to be 70.8 milliliters of water to be added here. So just something to keep in mind, taking a look at what exactly is the question asking us to find. Is it asking us to find the volume of the solute, of the entire solution, or just of the volume of the water that we have to add? Each number has meaning, and it's up to us to be able to take it apart and decipher exactly what quantity these numbers are trying to capture. Our last measure of concentration that we're going to look at, called the mole fraction, is essentially just another percentage, but this time it's a fraction in relation to moles. It is the moles of one single component of our mixture divided by the total moles of everything present. You can think of this as a percentage, but it's really not taking the percentage because we are not multiplying by 100. Instead, we're just going to represent this as a proportion. So let's see two examples of using the mole fraction here. So our first example is looking for what mass of potassium chloride is required if we want to make a 1 liter solution that is 0.2 molar. So we're looking for mass potassium chloride with a target concentration here. So we know that our solution is 0.2 molar, and mass is going to be hidden in this mole unit because we have moles of potassium chloride and we want to make 1 liter of this solution. So if we rearrange this, we get that our solution is going to contain 0.2 moles of potassium chloride. Now we are looking for a mass, so we're just going to take our moles of potassium chloride, multiply by its molar mass, and that's going to give us the mass of potassium chloride needed for this solution to have that concentration that we're looking for. So this is just a quick recap of molarity and solutions, and now let's take a look at where the mole fraction can get involved in. Our question here, what is the mole fraction of potassium chloride? So our mole fraction given by the Greek symbol chi for potassium chloride is just equal to the moles of potassium chloride divided by the total moles. Now this is where we want to keep notice of what exactly total moles represents. In our aqueous solution, our total moles is going to be the moles of potassium chloride and also the moles of water. Now we already know that we're going to have 0.2 moles of potassium chloride. So we already have half of what we need. All that's left now is to find the moles of water. This is where it gets a little tricky. So we're not given really any information here about water. All we know is that we have 1 liter of solution and we know its density. So if we have the density of the solution, which is mass over volume, and we know the volume of it, we can find the mass of our solution. So the mass of our solution is just density times volume, which would be 1 gram per milliliter times 1,000 milliliters, which gives us 1,000 grams of solution. So here, you might be inclined to take your 1,000 grams and convert it into moles of water in order to find that. But what we again must keep in mind, it's a solution. There's 2 parts. This 1,000 grams includes the mass of not just water, but potassium chloride. We figured out in the first part that there are 14.9 grams of potassium chloride. So if the solution contains a total of 1,000 grams, then removing the 14.9 grams of potassium chloride leaves us with 985.1 grams of just water. Now that we have our mass of water, we can take this and find moles of water, and that's going to be our missing piece for our mole fraction. So 985.1 grams of water is equivalent to 54.7 moles of water. So now we can add that to our mole fraction and work this out, and we get our mole fraction becomes 0.0036. So our mole fraction, we want to keep in mind, is the total moles, which is the 2 components of a mixture, the solute and the solvent. Anytime we're working with these numbers, and just to reiterate, we want to keep track, what are these numbers keeping track of? Are they of just one component of the entire mixture? If we're looking for just one component of the mixture, well then we'll need to find a way to use what information we're given and probably subtract out another part from the total, just like what we did here to find the mass of the water.